Boa tarde a todos. Como toda segunda-feira, nosso programa se junta estudantes e professores para esse novo ciclo de palestra de nosso programa de pós-graduação. Hoje nossa palestra será ministrada por o professor Athanasios. Good morning, professor.
Good morning.
A professora Martini irá apresentar o professor, já que é um convidado especial dela. Então, professora, fique à vontade.
Okay, so let me introduce Professor Athanasios Laliotis. So he graduated in physics at the University of Athens,
yeah.
Okay, so just to say he's a Greek guy. He had his Masters of Science and Engineering at Princeton University in the Department of Electrical Engineering. I'm saying that because there is a lot of engineering in his trajectory. So I think it's interesting for us. His PhD thesis in Imperial College London on the theme of integrated optics. Yes.
Mm-hmm.
And after that, two postdoc, one in Paris, 13, where he's actually working, and another one back to Imperial College London for 2 years. Okay, on I didn't write it, but it's atomic ship, yes?
Atomic ships. Yeah.
Mm-hmm, atomic ships. And he was also invited professor into two good universities, once in Universidade de la República, Montevideo, e outro, é uma muito boa universidade. Yeah. And the other is Nanyang Technological University of Singapore, where he spent sometimes as an invited professor. Okay, so and since 2008, he's working in Paris 13 in this team. Okay, working on atom surface interactions. 2019 is professor at universities. And so his lines of research are around about interactions of atoms and molecules with surfaces in some systems, some very different systems. So I have written here atomic ships, nano-confined atomic vapors, thermally excited surface modes, and atom metamaterial hybrid devices. So I think he will talk more to us about his research now and what he has been doing, okay, as a researcher. So Athanasios, your turn to talk.
Thank you, Martin. Thank you for the invitation. I'm going to try to share my screen, and please let me know if you can see it.
Yes, we're seeing.
And you see a full screen. Okay. No. So, yes, thank you for the introduction. Like you said, I'm working in the University of Paris 13, which is actually now called Université Sorbonne Paris Nord. It's a little bit to the north of Paris. So I'm working in a group that is mainly focusing on the spectroscopy of atoms and molecules in confined spaces, really close to dielectric surfaces. And we do these experiments primarily to have an experimental measurement of atom surface interactions, and measure in particular the effects of these interactions on the atomic energy levels. So I will...
Sorry, Athanasios.
Yes.
Maybe if you try to put use all the screen, it will be better.
This one?
No, I mean, we have your side slides in the corner, so
full screen.
the full screen will be better if you can.
If I do what if I share both screens? Sorry. So what do you mean?
I mean, I could show your presentation, but it's not the full screen. It's partial.
It's not full screen. Okay,
So it's okay, but it will be better if you can see.
Yes, it's true. It's true, but I put it on full screen. So let me see. Let me see again. Infinite. So now I am in full screen, but not for you. I'm not in full screen for you.
Oh, you need first put in full screen, and after this you need to share your screen. First, before to share your screen, you need to put the slide in full screen, and after this sharing your...
Okay. I'm trying to do this, but I'm not sure how to do this, because if I'm in full screen, I cannot see the window. I don't know. So
It's okay. It's okay.
I am. Wait. Does that work?
Nope.
Nope. Oh. Does that work?
Nope.
Nope.
Go ahead. We can see. It's okay. It's clear.
All right. Okay. Sorry, but I cannot get it to work. All right. I will put it in full screen in my screen, and then okay. So all right. So I was talking about atom surface interactions. So I'll give you an outline of my talk. I will first try to explain a little bit what it is, this physics of atom surface interactions that we normally call Casimir-Polder physics. I'll give you a general introduction. And then I will speak a little bit about the experiments that we do here in Paris. There's a spectroscopic experiments to measure these interactions. So this will be a general introduction on the subject. And then I will speak a little bit, I will go into more detail in two experiments that we're doing at the moment. The one includes Rydberg surface interactions. So Rydberg atoms are really very highly excited atoms, where the electron is very far from the core. And I'll tell you why these experiments are interesting, why we're doing them, what we hope to measure. And I'll give you sort of a report, or like an ongoing report, progress report on where we are at the moment. And then I'll speak a little bit about a new experiment that aims at probing molecules next to surfaces. And I'll tell you why this is interesting and what we're doing at the moment. Okay, so I'll start by giving you what I think is the simplest description of what the interaction between an atom and a surface looks like, and it is essentially the interaction of two dipoles. It's a dipole interaction. So the atom is an electrically neutral object, but it has an electron that goes around the core that is charged, and this creates a dipole that is fluctuating. So a dipole, there's a plus and there's a minus, and it
Athanasios,
So,
sorry to interrupt, but we are still at the first slide.
Okay.
We didn't see the outline.
okay, good now.
Okay,
It's
good.
good now.
Now it's good.
Yes.
Okay. When I'm in full screen, I guess. Okay. All right. When I'm in full screen, you cannot see it as I go down. So all right. So this is the atom. Then the atom is electrically neutral, like I said. But since the electrons go around the core, there is like a dipole, like a fluctuating dipole moment. And if you put an atom very close to the surface, if you put this fluctuating dipole of a dipole moment that goes around, you have a plus and a minus, and this will, and the existence of the surface will create an image. Okay? This is just a purely electrostatic approach on this interaction. And this image will have a minus and a plus, an opposed dipole, and this will create a force between those two. This is an electrostatic force that you can use by using simple electromagnetism. And if you do the calculations, you'll find that the energy of this dipole, due to the interaction with its own image, is given by this formula, which is d squared plus dz. So this is the dipole moment squared, and this is an anisotropic interaction that depends on the orientation of the dipole, and it's 1 over z to the cube. So this is an interaction energy, and this interaction energy, one of the things it does, it creates a force, obviously, but it also shifts perturbs, if you want, the energy levels of the free atom. So the energy levels of the atom when it's close to the surface are not the same as they are when it's far away from the surface. And one tool that we have in order to calculate the new energy levels is perturbation theory. And if we do perturbation theory, we can actually calculate the energy shifts. And this is done in quantum mechanics by taking this sort of the expectation, the average value of this operator. And this depends on the average value of d squared, which actually, if you do some mathematical tricks, it ends up that it is a summation over what is called the dipole moment matrix element between two states here, to the square. So it's a sum essentially on all the allowed dipole transitions, but in reality there are only a few of them that count. There are only a few transitions, only a few wavelengths that actually contribute much more strongly in this interaction. So in any case, to make a long story short, what happens at the end of the day, you get a shift that depends on minus C3, which is called a van der Waals coefficient, over Z3, which is the distance dependence, where Z is the distance from between the atom and the wall and the surface. C3 is a parameter that depends also on the dielectric properties of the surface, okay? But it also depends on the actual atomic state that I'm probing. It's actually bigger for highly excited atomic states because the dipoles are bigger, because the electrons are further away from the core. Okay, this is a simple image, but I would like briefly to introduce another sort of point of view, which was introduced by Casimir and Polder for the first time. And they described the interaction between the atom and the surface as a quantum fluctuations problem. So quantum fluctuations are fluctuations of the electromagnetic field even at zero temperature, okay? And the most classic example that actually Casimir also introduced is the attraction between two plates. So actually, if you have two plates, you can see here, I'm very bad at drawing, but you can see that the modes of the electromagnetic field are not the same inside the cavity created by the plates as outside. So there will be an electromagnetic pressure due to these quantum fluctuations that actually tends to pull those plates together. And you can use the same type of argument to describe the atom surface interaction as an interaction of the field with the fluctuating vacuum. Okay. So normally, the interaction between two plates is nowadays called Casimir interaction, whereas the interaction between one plate and one atom is called the Casimir-Polder interaction. But these interactions are strongly related, and they're due to quantum fluctuations. So this description is slightly different. It's a kind of quantum electrodynamics description, so it's a little bit more complicated. The theory is a little bit more complicated. But what is important to retain here is that actually when you go very close to the surface, when the atom goes very close to the surface, at distances that are much smaller than the typical transition wavelengths, then you recover this formula, which is the electrostatic formula that I explained in the beginning. But if you go very far away, you have some different behavior, and this different behavior actually is minus C4 over Z4, so the power law changes. And this is what usually people call like the far field regime. So this is a new description of the interaction. Okay. And just to give you some idea about the history, this behavior that deviates from this electrostatic approach, that gives you a more QED, a quantum electrodynamics approach of the Casimir-Polder interaction, was first demonstrated experimentally in the 90s, okay? And it was done by ground state atoms that fly through a gold cavity between two sort of plates. So, and then actually what they measure here is they measure the number of atoms that goes through. So like the stronger the interaction, the more the atoms will stick to the walls and the less will actually fly through the cavity. So actually if they do a little, theoretical analysis of the experiment, they measure the transmission as a function of cavity width, and they actually realize that the van der Waals interaction, the electrostatic interaction, the C3 over Z3 interaction does not fit with the data, and they do have to take into account the quantum electrodynamics effects. And this is what gave rise essentially to what we call now the Casimir-Polder interaction as a unified sort of theory of atom surface interactions. So if you want, I can give you an idea for a different atom, like I'll take that I'll be using later on. This is the cesium atom in its ground state. So I can plot you the energy, the shift, the interaction energy between the cesium atom and a sapphire surface. So this would be the full Casimir-Polder prediction. And this straight line here would be the van der Waals approximation. Let me just point out that I'm plotting the energy multiplied by Z3. So a full van der Waals approximation would be a straight line, but the real potential is not a straight line. It deviates, as you can see, it deviates a lot from the electrostatic approximation. So that's what's going on for ground state atoms. But in my experiments, I'm not focusing on ground state atoms. Actually, I'm focusing more on excited state atoms. And I would like to tell you why they can be interesting and why they're different. Okay. So one reason that these ground state atoms are different is because these excited state atoms are different, is because that when you're in the excited state, you have also spontaneous emission. So the atom can decay from this state and go down to this state. In particular, for example, in cesium, you have the first excited state at 894 nanometers. These are sort of optical wavelengths. And this spontaneous emission couples the two levels and essentially creates a little oscillating antenna, almost like a classical antenna at this sort of wavelength. And actually this creates a whole different sort of behavior, because of course, if you have an oscillating antenna that moves away from the surface, that is interacting with its image, actually the field, the reflected field, can come in phase, out of phase, and in phase and out of phase with a period that's actually related to the wavelength. and it can lead to attraction, repulsion, and things like that. So it's a much more exotic behavior that actually excited state atoms can have as a function of distance compared to excited state atoms. And additionally, of course, I don't have like a zoom here, but if you zoom here, you would find that very close to the surface, excited state atoms are much more faithful in some sense to the 1 over Z3 law than ground state atoms. Okay, this is a sort of very general introduction. And moving a little bit forward, I would like to speak a little bit about our experiments. What do we do here in Paris in order to probe the interaction of excited states? That excited states that are actually short-lived because they de-excite due to spontaneous emission. So the spectroscopy we use is actually inside the vapor cells, like atomic alkali vapor cells. And the spectroscopy we use is based on reflection spectroscopy, in contrast to normal sort of transmission spectroscopy, where you would actually probe the absorption of the atoms at a resonant frequency. Here we actually measure the reflection between a window, a dielectric surface, and the vapor. And we are not sensitive to absorption, but we are sensitive to dispersion, meaning that we're sensitive to the refractive index of the vapor. And the refractive index of the vapor changes as you scan your laser around the atomic resonance frequencies. So the reflectivity of our laser will change when we scan the laser around the resonant frequencies. And this is what we measure. And this is what we call selective reflection spectroscopy. Selective reflection spectroscopy is really, it's a little bit more, it's a bit complicated, so I will not go into the details. There are a lot of actually effects, transient effects of interaction between the atom and the electromagnetic field that need to be taken into account. But what should be retained is that it's actually a spectroscopy that probes atoms close to the surface. Obviously, it's a reflection, it's an interface problem, it's not a volume problem, at distances that are related to the wavelength, okay? And of course, it's not of course, but it's also, like, you should keep in mind that it's also a sub-Doppler spectroscopy, meaning that it's basically sensitive to atoms that are slow close to the surface, and therefore it's a high-resolution spectroscopy. It's not very much sensitive to the Doppler effect. So just to give you an idea of the experimental protocol, what we do is we take our lasers, we scan our lasers around a given transition, we take the spectrum that we actually measure, and we have a kind of elaborate theoretical model. We use this model to fit the spectrum, and from this we extract the C3 coefficient, so which gives us the atom surface interaction, which is C3 over Z3. This is the protocol. I'll give you some idea of what the signals look like, okay? This would be a direct signal of selective reflection. So this would be a Doppler broadened signal, or selective, like a dispersion signal here. And this spike that you see here would be a more pronounced, a stronger contribution from atoms that are slow. If you want to increase the contrast of this narrow contribution, you take the derivative. So, and you do this by some experimental techniques that is called FM, frequency modulation. So when you actually take the derivative, you see something that is very narrow, and the line width of this narrow thing is the homogeneous line width that is defined by the lifetime and, of course, by collisions that atoms do between themselves. So this would be the signal without van der Waals interactions, but actually if you start including van der Waals interactions, Casimir-Poldor interactions, then you find that your signal is actually shifted and it's also distorted. And this would be evidence of this type of interaction. Okay, so this type of experiments were not actually very new. As you can see here, you might recognize some of the authors, the first authors that sort of presented the first measurements of selective reflections. So it's Marcos and Martina that did experiments on the cesium lines. So this one is the sort of D line, the T2 line of cesium, measuring the C3 coefficient here of about 2 kilohertz micron cube. So this is the shift induced by the surface. And also at another more highly excited atomic state, the 7p3 halves at the blue sort of transition, giving higher van der Waals coefficients. Just briefly meant to mention that it's also a selective reflection has also been used to probe excited state atoms that are actually coupled with surface resonances, related with polariton or plasmon resonances of the surface. And this has allowed us to show some exotic effects such as repulsion or temperature effects, but I will not be going into further detail concerning those experiments. Okay, I will talk a little bit about Rydberg experiments, and I will tell you first why. Why we want to do such experiments. So let's take, for example, this is the cesium-7d atom that we used to measure the temperature dependence of a Casimir-Poulter interaction. And let's look what happens if you increase the principal quantum number, if you increase the excitation, if you take the electron further away from the core. So what happens is that the atomic radius the radius of your atom depends on the principal quantum number squared. Okay, so for the 15D, for example, level here, the atom is many more times big. Let's say this is 2 times, and this is 4 times bigger radius. So the atomic clouds, as the atomic clouds become bigger and bigger, the dipole moment also becomes bigger. The dipole moment square now would depend on n to the power 4. So eventually the van der Waals coefficients would scale as n to the 4th. So when you increase the level of excitation, okay, by a factor of 2, you gain more than an order of magnitude in atom surface interactions. So you actually start probing huge interactions of the atoms with the surface. This is something that we've never done before, and this is something that we thought it was very interesting to study. But it's not just the fact that the interactions are huge. There's also another thing that is sort of hiding behind it. And the idea now is that the atom is no longer a point dipole, but it actually has a size that is almost comparable to the size of the atom surface distance. So you cannot no longer consider it as a point dipole, and you actually have to take into account higher order contributions to the energy, to the electrostatic energy, or to the Casimir-Poulter energy. And the first one that counts after the dipole one is actually the quadruple one that has a different dependence, and it depends as minus C5 over Z5 instead of C3 over Z3. And this one, this coefficient here, also depends on the principal quantum number, but here to the power of 8. So as you increase the excitation, you increase the importance of this factor, or if you go closer and closer to the surface, you increase the importance of this factor. And this factor, the quadruple sort of term in the interaction, is actually a term that has never been explored experimentally or never been shown experimentally before. And this is why we want to study it. Well, this is why we want to sort of experimentally probe atom Rydberg surface interactions. Okay, few words about the theory and how we actually do the calculations, because we need some theoretical predictions to actually see what coefficients we are supposed to expect. So in this case, for atoms that start to be highly excited, there are no let's say, precision calculations, and there are really not many experiments that actually give you the atomic parameters that are important, such as the sort of dipole moment. But what is good is that Rydberg atoms, because the electron is very far away from the core, they behave kind of like a hydrogen atom. So actually, you can go about and using sort of atomic physics, let's say a master's level atomic physics, you can actually calculate the wave functions, the electronic wave functions of the Rydberg atoms. And once you've calculated the wave functions, you can actually go and measure the energy level shifts and the C3, so not measure, but calculate straightforwardly the C3 coefficients, which depend on the dipole moment. And you can do the same for the C5 coefficients that actually depend on the quadrupole moment of a given state. So here in our case, for the 15D atom, which is a sort of relatively high excited atom, we get a C3 coefficient that is now 5 megahertz micron cube. Okay, this is orders of magnitude higher than what we've measured before. And you get a C5 coefficient that is 2 kilohertz micron cube. This is smaller, of course, at 1 micron, but don't forget that it increases much, much faster with distance. So if we probe close to the surface, then we will we could be able to see it. Okay, let me just say a few things about the experiment then. So what we want to do is we want to perform selective reflection experiments on the cesium 15D line. So the way to access this line is a two-step, two-photon transition. So first you go to the first excited state of cesium with a 894 laser, and then you use a probe laser at 512 nanometers, a green laser, and you scan it around your transitions. Okay. So by exploring the spectra that you obtain in this laser, you can actually gain some information about the C3 coefficient. So let me show you the picture of the experiment. So what you have is you have two lasers. One is the green laser, that's the probe, and that's the infrared laser, which is the pump. The pump is actually stabilized on the transition that you want, the 6S, 6P transition. You mix them together, and you do selective reflection on a vapor cell. This is a vapor cell. There's a drop of cesium here, solid cesium, and the cesium is in vapor pressure, sort of inside the cell. If you want to increase the vapor pressure, you keep on heating up the reservoir, and then you heat up the cell as well to avoid any condensation. So this is your cell. You do selective reflection, and also what you do in this case, you also have an experiment in the volume, okay, that gives you the atomic resonances far away from the surface. Okay, so this would be how the pump probe scheme would look. That gives you sort of frequency references in the volume. Well, if you want to know more about it, you can sort of ask me questions later. I will just try to move on now and try to explain the selective reflection part, which happens here on this cell. Okay, so this here is the first spectra that we actually measured. So you cannot see much, and you cannot see much because the Rydberg transitions are actually not very strong transitions. They are actually weak transitions, and the signals are relatively low. So any signal that you might have in this curve is actually buried in noise. Okay, so the way to fight against noise in your experiment is to actually control very well your parameters, to control the frequency of your lasers, and to perform the experiment many, many times, to do an averaging. And if you do this averaging, you can actually, the actual signal that is hiding inside the noise can emerge. So this is what we did. And from this curve that I'm showing you now, we obtained this one. This is the signal of the transitions that you can actually see here. These transitions, the 6P, 7D transitions, both hyperfine components are actually here probed. So the laser is scanned around this one, and you can see two lines. These are the two lines that we actually see. So this is the experimental data. This is the experimental spectrum, and as the protocol sort of dictates, what we have to do now is try to use our model in order to extract the C3 coefficient and see if this fits with our data, with our predictions. I'm sorry. So this is what we get. The first fits that we tried looked like that. So you cannot have a very good fit in this case, and this is because our model made some approximations that assumed that the Doppler width is actually very wide compared to the homogeneous width, and actually also the Doppler width is much smaller than the van der Waals interaction. So these approximations are actually not really valid in our case, but therefore we tried to tune our models, and actually we used a much simpler model of just simply ignoring the atomic motion, because it's probably not so important when you actually have interactions that are very big. And we get this sort of fit that looks much better. Of course, we get C3 coefficients that actually are bigger than what we have predicted, which was 5 megahertz micron cube, not 10 megahertz micron cube as we actually measure. But we're actually in the process of refining our models in order to extract better sort of experimental predictions and see if they match our theory. So this is sort of what I wanted to say about the Rydberg surface interaction experiments. So actually at the moment, like I said, we're trying to interpret better our data, to develop our models to get better predictions. And of course, we're trying also to go towards higher Rydberg states, and eventually maybe experiments inside thin cells that actually can be used to control the confinement instead of selective reflection that I explained. Okay, so that's the Rydberg experiment. So now I think I have some time to talk a little bit about the new experiment that we're actually doing, which is probing molecules next to surfaces. Why do we do these experiments? Obviously, there's one motivation that concerns Casimir-Polder interactions, molecule surface interactions, instead of atom surface interactions, like I did before. And there's some motivation for this, like molecule surface interactions are actually much richer in terms of physics compared to atom surface interactions, because the molecule has an internal sort of structure and internal geometry. And you can actually have effects such as anisotropic effects, meaning that the interaction would depend on molecular orientation. You can also have some other effects that include the chirality, the chirality of molecules that have been studied by theoreticians, but so far they have not seen any experimental sort of demonstration. Another interesting thing you can do about molecules is actually make compact frequency references. So if you actually manage to probe molecules in small distances, you can actually use their series of row vibrational lines in order to actually pinpoint the frequency of your lasers. And in particular, people have been using, for example, hollow core fibers that are filled with acetylene molecules, or waveguides that are actually in the vicinity of acetylene molecules again. And if you actually do this, it turns out that you can have and acetylene has lines at 1.5 microns, and therefore you can use these systems to actually have a compact frequency reference, which is good for applications. So, like a few words about the experiment and molecules. So what you have here is molecules usually are weaker, have weaker transition probabilities, because we are actually probing row vibrational lines. So we're actually putting the molecular core in vibration or rotation, and we're not exciting the electronic cloud here. And actually, there's a partition function, meaning that the ground state, the ground molecular state, it actually contains a lot of rotational states, and therefore the population, the molecular population at thermal equilibrium contains a lot of these states. So essentially, when you try to probe them, it's much more difficult. This is what's important. But what is also important to remember is that actually, even though the signals are weak, the molecules have a very, very long lifetime. Therefore, they have a very, very narrow line width. And their line width essentially depends on the pressure. Okay. So in our case, we started working with SF6 and NH3 molecules. These were our sort of molecules of choice because they have really strong transitions, and this is where we thought that we had the most chances of observing something or observing a signal. This is a schematic over the setup. What changes here is actually the wavelengths. So the wavelengths we are here, actually, I forgot to mention that we're using 10 micron transitions. So this is the wavelength. So in order to access these transitions, you need to use QCL lasers at 10.6 microns. These work very well in contrast to old lasers like CO2 lasers. They're very compact and very simple to use. And the sort of novelty here is that the cells are no longer sort of glass cells with drops of cesium, but it's actually like made out of vacuum components, and the molecules just come from a gas bottle. So essentially, you open your gas bottle and you can put in as many molecules as you like, and then you can just take them out by just sort of opening a valve and taking out the molecules. So otherwise, the experiment is the same. So you have the first experiment here is a selective reflection experiment on the molecular cell window, and you also have frequency references in the volume that allow you to sort of compare what's going on in the volume and what's going on in the reflection close to the surface. So to our surprise, we actually managed to see some signals. These were observed like a long time ago. So we started off by using really sort of high pressures. And at these high pressures, you actually have like a lot of collisions. So when you have a lot of collisions, you have like a lot of broadening. So this sort of gray line is actually at 1 torr pressure. And the goal, once we observe the first signals, is of course to actually reduce the pressure. And when you reduce the pressure, you eventually start reducing collisions and therefore the line width. You increase the resolution, and this is favorable for performing molecule surface interaction measurements, also for performing for frequency reference applications. So this is what we're trying to do. This is the line. This is a 200 millitorr sort of pressure. At this pressure, the collisional line width is about 5 megahertz. And here you can also see the structure of the transition that we are probing. There's a hyperfine structure, and this hyperfine structure has in the order of megahertz. So as you reduce the pressure, you start seeing, now you start being sensitive to the hyperfine structure, and you see like these features here that are due to the hyperfine structure. And eventually you see them much clearer when the pressure becomes very low and the collisional line width is now sub-megahertz. Of course, here you will notice that the line width is actually limited by the laser. The laser has its own sort of line width, and this is actually what the best thing we can do with our current setup, but we sort of reached the limits. The line here, the black line, is actually a theoretical model that does not include any interactions, and you can see that it fits very well, which means that for the moment our signals are compatible with a sort of no atom surface, no molecule surface interactions included. So what we wanted to do is to actually see to what values of the C3 coefficient our experiment excludes. So if you want to do this, you actually take the fit, you fit with a C3 coefficient that is very big, for example, here 500 kilohertz, and then you see that this obviously doesn't fit, and then you start reducing the C3 coefficient, and you do at 100 kilohertz micron cube, and then you see that this starts sort of approaching your curve. And then at 10 kilohertz micron cube, you can almost have those two curves that actually look the same. There's still a bit of difference, but we estimate our experiment to bound the C3 coefficient of the molecule surface interaction at between 0 and 10 kilohertz micron cube. So the way we can do better is actually by reducing the laser line width, so we can have better resolution, or by changing the molecule and finding a more favorable molecule. And we're actually performing now calculations with theoreticians that will allow us to go further into these experiments. So just very briefly, I would just like to spend 5 minutes to tell you about another nice application that we discovered for selective reflection. Actually, molecular spectroscopy is a very sort of open and vast field, and there are some molecules that are of interest, in particular, for example, heavy molecules, such as the SF6 molecule, that are actually interesting. They're greenhouse gases, and it's very interesting to know accurately their spectroscopy, meaning the frequency position of their transitions, and also the amplitude of the transitions. And actually, if you know these parameters, you can actually measure how much SF6 you have in the atmosphere, and how much you can potentially heat up the atmosphere. So there are sort of databases that give you these things, but actually they are very, very incomplete, especially in the case of SF6 and other heavy molecules. So we tried to sort of add something into this sort of respect, and show you some spectra we got for SF6. This is SF6 spectroscopy. This is saturated absorption spectroscopy, a sort of spectroscopy in the volume, and this is selective reflection spectroscopy. Notice that these are like longer scans with a lot of transitions, and actually saturated absorption spectroscopy gives you a higher signal-to-noise ratio, and therefore allows you to pinpoint the frequency positions of all these transitions. But selective reflection is a linear spectroscopy, and therefore allows you to pinpoint the amplitudes much better. So you can use those two in tandem to actually get information about the frequency positions and the amplitudes. And the way you do get information on the amplitude is by actually doing the fits that I explained before. You ignore the interactions, the molecule surface interactions, because they are not very important in this case. And you actually see that you have very good fits, and these fits allow you to extract transitions in intensities and, of course, frequency positions of the transitions. So just to tell you, just to give you an idea of what the database is actually predicted for the SF6, and this would be what our experiment gave. So these are the transitions. This is the simulated spectrum that we get if we actually find the positions and the amplitudes of all the transitions. And this is what the database predicted. Okay, so this is much less transitions that were not known, well, I mean, we were able to pinpoint them with this experiment. This is not a usual application of selective reflection, but we found out that that was kind of interesting. Okay, I'm going towards the end of my talk. I'd just like to tell you a few things about the future of the molecule experiment. So what we are doing now is we're actually fabricating thin cells. And thin cells are actually fabricated in the following relatively simple way in our lab. We take two windows. Instead of taking a big cell, like we take two windows and we put a little spacer between the windows here. And this spacer has a thickness of micrometric thickness, okay, or like maybe 100 nanometers or 1 micron or whatever we choose to do. And we actually sandwich those two together, okay, and we put it in vacuum. And this would sort of, and then we use the hole here to actually put molecules inside. So when we probe the molecules inside the thin cells, actually they are strongly confined by the thin cell windows. Okay? And this allows us to actually control the thickness and measure molecule surface interactions, because we are no longer bound by the wavelength of the light. We can just make very, very thin cells and therefore measure the the Casimir-Polder interactions. And eventually we can actually make compact systems that actually give us the transition frequencies, and they can allow us to make frequency references. And actually this is actually a picture of the thin cell that we actually fabricated in our lab. So these are the windows, and this is the sort of hole that on the other side that allows us to put in molecules or pump the cell depending on what we want to do. This is actually a signal, like an SF6 signal, like comparable to the one I showed you before with selective reflection, but this one is actually much better. It's like 10 times bigger, so it's much more favorable. It's a compact system, and also nowadays we actually managed to have signals with acetylene molecules, meaning that we have frequency references at acetylene row vibration. Have row vibrational transitions at telecom wavelengths, which is also very interesting. So in conclusion, of course, with molecules, we can go towards fundamental physics measurements or sort of applications such as compact and simple frequency references or sort of molecular spectroscopy for enriching the molecular databases. So this would be the end of my talk. I hope I haven't abused my time. Just to acknowledge a little bit my colleagues, of course, well, not a little bit, I have to acknowledge my colleagues because we're working here together, in this together. So Biplab Dutta is actually the PhD student that is working on the molecules. Guadalupe Garcia Arellano is a postdoc, a new postdoc that's working on both experiments. And the other permanent members of staff are Isabelle Morin and Daniel Bloch that work with me in these experiments. And of course, it's João Carlos de Aquino Carvalho is actually a PhD student, used to be a PhD student and a postdoc in our lab, and he's actually contributed a lot in both of these works. And we have, of course, various collaborations inside our lab, but also external collaborations with Stefan Schill, a theoretician that helps us a lot with calculations, but also with José Rios Leite, which is in Recife, and Martin Chevrolet, Marcos, of course, that contribute to our work whenever they come and visit our lab. So that would be it. Thank you very much for your attention. I will stop. Well, I don't know. Should I stop the... Do you see my screen now, or do you see my face? I don't know.
Okay.
Okay.
So now what do you see now? I'm sorry, like, do you see my presentation, or do you?
No.
No, okay, all right.
No, it's dark.
Ah, it's dark.
Yes.
So now you see me.
Yes.
Well, if you have a question, then I can sort of share the screen again, but it's a little bit uncomfortable for me if I don't see your faces. So yes, if you have any questions, please feel welcome, like, to ask.
I have one. It's a detail about the spectroscopy of Rydberg atoms. Maybe
Yes.
I didn't pay attention. I wanted to know what the temperature and densities are.
So the temperature and densities. So the temperature. Let me just put this this thing back so I can show you. Infinite. So the temperatures here, we're not using very high temperatures. This would be the cell, okay?
Yeah.
The temperature of the body would be around 200 degrees, well, maybe 250 Celsius.
Okay.
And then the reservoir, we heat it up to 150, 170 degrees, and this would correspond to about 10 millitorr pressure of cesium vapor inside the cell. So it's kind of a high density experiment.
Okay. Only wanted to know if you had to heat it really, but you don't have to.
No, not the cell itself, but then the reservoir, of course, it's like the pressure is kind of high because eventually it helps us in order to get a signal there.
Okay, maybe I have a technical question about this. I love this small cells, thin cells. Did you make some measurements or interferometry to?
Yes.
How? Yeah.
We did. So this cell that we actually made is so the thickness that we were aiming was about 5 microns. And the reason we were aiming at 5 microns is to have a λ/2 thickness and to observe the Dickey effect. So the spacer that we used was actually a sort of gold thin sheet, like not an aluminum foil, but a gold foil, much more expensive actually. So we cut it in a sort of annular sort of geometry, and this was about 5 microns, and we pressed it together. And then we did interferometry to actually have a better idea of what the thickness is, if it was what we expected, and how much it varies actually around the cell. So we did interferometry, Fabry-Perot interferometry, with different wavelengths. So we did we used all of our lasers, like we did 852, 894, 1.5, 10 microns. So we sort of we used all of these lasers to actually measure the reflectivity and the transmission, and therefore extract what the thickness would be from interferometry. So this way, it turned out to be 5.35. Plus or minus, I don't know, like not even 50 nanometers. So it was pretty uniform throughout the surface of the cell.
Okay.
And the surprising thing is that they actually just worked. They just worked. Like when Joao was here, like he was the first one to actually test them, and I think it's been one of the easiest experiments that I.
It's fluid or just?
So actually, that's also a good question. So in the beginning, we just apply pressure. We just apply pressure by screwing it. Like I showed the picture. I don't know, like again. Yeah, okay, but you just screw the screws, like, and you apply pressure. So the idea, what we wanted, was that it would work like that. Like, but we found that there were leaks. Like, if we just did it like that, we applied some pressure, there were leaks. Like, we couldn't get the vacuum when we were pumping. We couldn't get the vacuum. So eventually, we ended up putting some glue around it. And this worked. And it actually sealed the cell, and you can get the pressure down, and you can have we can have the molecules.
Okay.
Yeah.
And maybe a last question about this atoms very close to the surface. Very long time ago, we tried to use evanescent waves to guide the atoms in a well-controlled distance from the surface.
Mm-hmm.
Okay, did you try something? You used to have cells with a prism in the...
Yeah, maybe, I don't, but I have never worked, personally, I've never worked, and I never really thought about evanescent wave spectroscopy. That's what you're referring to. I'm not sure if you can be...
No, just to be precise, the evanescence waves was to guide the atom, and the problem with normal...
No, we never tried. No, we never tried such schemes. Well, for the moment, in the cells that we have, it's not possible, but so you could put some sort of detuned laser to actually put them. Yeah, this could be an idea. This could be an idea.
Yeah, I give up atom physics in Brazil, but I love it.
Well, you can come in Paris and we can do it together.
Sure. Yeah. Okay. Thank you, Athanasios.
Any question? Alguma pergunta, professor? Professora Martini, você quer falar alguma coisa?
No, I liked the presentation very much. There are some things I knew, some I didn't, and it's really very interesting. So they have. I was looking at. You spoke, Athanasios, about your results on these molecules as if they were kind of preliminary. But you have a very nice paper published recently.
Oh, if the preliminary are PRL, so...
I was wondering what kind of... I didn't read the paper, but I was wondering what is in this paper. It is what you presented us, yes?
Yes, it's pretty much these results. Yes, like the results on NH3 and SF6, and well, stressing the possibility of Casimir-Poldor measurements with molecules, but also stressing the fact that these measurements can also be interesting for other purposes, such as molecular spectroscopy, which is something that we didn't expect, I have to say. Like when you're doing atomic physics, you're used to seeing a database, on the atomic frequencies, and you know that you trust them, and that's it. But actually, with molecules, it was not at all the case. Like we found out that people don't know the spectroscopy of molecules, and we could contribute something. So we talk about this possibility in the paper as well. And that sort of seems to have convinced the referees of the importance of the technique. But it's an ongoing work. I mean, it's measuring the interactions with the surface it's a goal that we want to go to. And the thin cell approach, I think, is the most promising approach for this experiment. But also we have a new an ongoing project with metrologists like telecom metrology that actually think that these thin cells, so if you actually probe acetylene row vibrations, they can be used really used for frequency referencing and applications. So we have a new sort of project with some of the people in the lab that we would want to actually take a thin cell and maybe lock a laser, like a telecom laser, and measure the stability that you can obtain by this system. So it's an ongoing work in terms of this. So I guess, you know, like, I mean, the PRL is just published, but we finished this work 2 years ago. So now I'm just thinking about the future.
Okay. Very nice. A lot of work ahead.
Yeah, it's the molecule thing is keeping us busy. Yeah.
Very nice. Thank you, Athanasios.
Thank you, Professor,
for the invitation.
for the invitation.
Right, for giving me the chance to. I would rather do more, actually, I have to say.
Please open the microphone. Vamos agradecer ao professor, né? Batendo nossas palmas ao estilo português.
Very nice.
Thank you very much. Thank you.
Okay. Thank you, Athanasios. Nice to see you.
Good to see you.
Good morning.
Good to see you again, and well, have a nice evening.
Yes.
Okay.
Bye
And
bye.
good night for you.
Bye bye. Good night.
Goodbye.